Hello everyone, my name is Caroline Morton. I'm a software engineer and an epidemiologist, and I used to be a GP, and I'm really excited to be doing this presentation on polars, the gateway drug to Rust, and I'm hoping to give you some insight into why Rust is so amazing. This talk is specifically aimed for people like me who've come from a Python background or an R, more of a data science background. And so you'll see a lot of the examples I'm going to use are going to be involved in sort of dealing with different types of data. Okay, and polars is a library that is written in Rust, but you can call it from various different languages, including Python. And all of my examples today are going to be in Python. Who am I? So I've briefly introduced myself already, but I am a Python and Rust developer, an epidemiologist. I have a startup, which is called Yellowbird, and we make a product called Clinical Metrics, which is a medical simulation program. I used to be a GP, and I am now doing a PhD in synthetic data, which is being sponsored by Surreal. I'm also one of the authors of Async Rust by O'Reilly, which should be coming out later this year. And we're very excited about that. Okay. So, polars. We're going to start talking about polars and how it can be used in data science. I'm going to move on to talk about how I specifically have used it in my day job, which is at Queen Mary University on a biobank, and how it was really great for getting huge performance improvements. And then I'm going to use that to talk about Rust and why Rust is awesome and we should all learn Rust. Okay, so let's start with polars. So polars is a fast multi-threaded data frame library. It's most similar to something like pandas, and actually as you start to use it, it will seem very familiar to people who are pandas users. It's based on data frames or tables, and is essentially designed for high performance data manipulation and analysis. It's an open source project, and as I said before, there's support for Python and Rust. So this is what it looks like when you go onto the polars website, and they've got great documentation. And if you just Google polars and then pretty much any question you want to ask, there'll be an answer. It's less good, I will say, with ChatGPT at the moment because it is quite a new library. So a lot of the features that they've implemented are not included up until when ChatGPT has been trained on. That obviously will change in the future. Okay, so one of my favorite things about polars is it's so lightweight. So it has 0 dependencies. So when you install it, if I install pandas, for example, it installs a bunch of other stuff. Not much, but if we compare the list, we have quite a few different packages get installed as part of pandas, including NumPy, and they're quite big. Whereas if we just install polars, it's just one library, it's pretty quick, and so that's really nice. It is able to handle larger than RAM data, and if you just think about that, that is very, very cool. So you can actually work on data sets that are bigger than the size of the RAM on your computer, which means it's able to optimize for your basically optimize for what data you're going to actually need to use or load to run your analysis, and that is extremely cool. There's this standard data test where I've put on the right hand side of the screen here, which compares basically it's a way of benchmarking some of these programs, and pandas at this point is 360 seconds to do this data task. I haven't gone into the data task, whereas polars is 11 seconds. So it's very, very quick. Okay, so for my example today, I'm going to be imagining that we sell fruit. We sell apples, oranges, and bananas, and we sell them to a variety of different customers, including restaurants, people, and shops. And it's just synthetic data. And I just created this huge data set. I think it's maybe 10 million rows. And if we want to do something like this, where we want to take this data set and we want to find what is the mean cost of apples, or the spend bought on apples by restaurants, in the top one is in pandas. So I'm doing a start and an end date time. So that's just allowing me to measure it. And you can see I've got some code and that outputs something, and it takes 3 seconds, 3.6 seconds. Whereas if I use it in polars, and you'll notice that it actually looks quite similar, the code, it's 1 second, 1.7. Okay. And you get, the same result. Except when you actually look at the result on the example which uses polars, you're actually getting way more decimal places. So you're actually getting finer data than you get with pandas, and you're getting it in this example for, say, a third of the time it takes pandas to do. Okay, so why is that? So I'm going to cover multi-threading, the column storage model, and some typing. So if we go to the multi-threading, I've used this way of measuring things called timeit. It's just part of the standard library and you can use it. And in this example, what I'm doing is I am loading the whole data set. And as I said, this is 10 million rows of data. Okay, and you'll see the way timeit works is it runs a number of iterations and it measures them and you get a mean. And if we just do the loading, you'll see that polars, which is the first example, is much, much quicker than pandas. Okay, and one of the major reasons for that is that it's able to use multi-threading. So we can use multiple threads, and we can demonstrate this if we override the max threads on polars, which you can just set as an environment variable. So if we overwrite it from, I think 8 is standard, don't quote me on that, to 1, you'll see that you actually get a difference in how quickly it gets loaded. So that's really cool. You don't get that option in pandas, and yeah, I just think as standard to use multi-threading is really excellent. All right, so we're going to move on to the column storage model. So polars stores its data in columns, which means that all values of a particular column are all stored together. This makes it much faster to access the data. So basically what this means is that the CPU is not having to jump around in memory. So I've got this picture which I just took from a Medium article, where instead of having to skip between different rows to find all of the data, we can just do it in columns, and that gives us I'd say it's a much better way of representing it, and for this particular purpose it makes it much quicker. Now there are obviously good reasons that you might want to have your data as rows, but in terms of speed and performance it really makes a difference here. Okay, and then typing. So Rust has a typing system, and since polars is implemented under the hood in Rust, we can take advantage of that. What the Rust compiler does, which I'll come into later, is it offers optimizations based on type information, and that happens at compile time, and it just means that it's much quicker. So if we look at two data frames, the first one is in pandas and the second one is in polars, they look identical. The data is slightly different, but the columns are the same. But if you notice on the polars one, you're also getting some information about the type. So for example, with customer ID, you're being told this is an I64, so a type of integer, and how much space that would take up in memory, and the same with string. Okay, and I'm also going to move on to talk about this thing that I talked about earlier, which is how this enables you to load data that is bigger than the RAM. So we're going to use this scan CSV. So instead of read CSV, we're going to use scan CSV. And what scan CSV does is allows us to have lazy execution. So basically, lazy execution is it doesn't do something until you say go. So it just would, in this case, scan it and see like what data do I need, and then that allows us to have optimizations. So in this example, we're scanning the CSV, that's the data that we want to load, and then we're going to do an analysis where we get the all of the apples bought by the restaurants, and we want to find out what is the average spend. And if we go through, actually nothing is really happening until we get to the collect, and the collect is essentially saying like, yeah, execute this. And then what Polars is doing under the hood is it's only using the data that would come in that query, and that means that it can work with data that's bigger than what it should be able to load. And that's very, very cool. Okay, so if I do that, we get a, as I said, we've got this microseconds, let's say 62. And then if I go into lazy evaluation, so the way that I was kind of taught about this is it's a bit like having you're going shopping. So you create a plan, like making a shopping list. You are optimizing the plan. So that's like organizing the shopping list. So you put all of the fruit together, put all of like the bakery items together, all of the tinned food together. And then when you go shopping, you're not having to like go through your list, in the order that you wrote it. You would just go and get all of the fruit together. You get all of the bakery items together, and so on and so forth. Okay, that's the way to think of lazy execution. And something similar happens when we're talking about Polars. So it's able to formulate a plan that's optimized. Okay, so what I'm doing here in this one, this is exactly the same query as we had before, but I've added in some timers. So I've still got the start, so that's we can start the query, and then I've got a before calculation. Okay, and if we do before calculation minus the start time, you'll see it's basically nothing, even though that's where the query is. And that's because it's not actually executing until we get the collect. And so until we run the collect method, it's not doing anything in terms of trying to load the data. It is getting that information. It's not empty code, but it's not executing. Okay, and so you can see that the majority of the time is in the actual collect, which is calculating the result, and then the average spend, displaying that to the user. Okay, so that's just a whistle-stop tour of Polars, and it's definitely something that you should look into if you're used to using pandas or some of the R packages. It's really good for dealing with big data. I've actually been amazed by how good it is, and even though I can use Rust, I'm actually quite a newcomer to Polars, and it was born from I needed the performance. And talking of that, I'm going to go on and say how I've used it. Okay, so I work at Genes and Health. So Genes and Health is a biobank. It's based in East London. We essentially, it's a biobank of people who are from Bangladeshi or Pakistani backgrounds, and trying to get them into studies, genetic and health data science studies. Generally, this population isn't that well represented in other studies, and so there's different processes of recruitment. So we have this biobank of genetic samples. Then we also have healthcare records from GP surgeries and from hospitals. They can be connected together. And then we have lots of researchers, including industry researchers, who come and do different projects with us. Okay, so we're dealing with lots of data. We have roughly 55,000 people in the biobank at the moment, but we have huge amounts of data, because if you imagine you've got at least one row of data every time you've visited your GP, and you would often have sort of 10 or 20, depending on what you've had done or what you've talked about. So we generate huge amounts of data. Okay, so the important thing background here is health encounters generate coded events. So coded event is not anything to do with code. It's just a numerical way of representing something like pneumonia or an antibiotic prescription or having your blood pressure taken. So they're based on something called SNOMED codes, which I'm not going to get into, but essentially every type of thing that you could think of has a SNOMED code in health. And this might be a way that we could represent, you've gone to your GP with a cough and they've taken your blood pressure and they found actually you've got signs of a pneumonia, you've been diagnosed with a pneumonia and you've been given some amoxicillin to treat that. Okay, so you've got a series of SNOMED codes. And so just from this one encounter, you've got 6 rows of data. This is what this will end up being across 2 different types of tables. So measurement tables and events get coded separately. So TRE Tools is the package that I have developed with my team, and it's called TRE Tools because we work in the TRE, which is a trusted research environment that also sometimes called secure data environments. And this is an open source project on GitHub, and you're very welcome to go and have a look at it. And you'll see it's in Python. It's a pip installable package that we have within the secure data environment, and it uses polars instead of pandas. Okay. So what I wanted to do was I wanted to take all of the different ways that you could represent different types of diseases as a ICD-10. So ICD-10 is a bit like SNOMED. It's a way of representing different health conditions. It's an international standard. And we have all of these different code lists of different ways you could represent, for example, pneumonia, okay? Because it's not just one code that represents pneumonia, unfortunately. That would make my life a lot easier. But it might be, say, 50 different ways that you might say pneumonia, like pneumonia with cough or, different types of pneumonia. And so we want to capture all of that information. So we have code lists, and we also have data sets. And the other thing you should know about NHS data is it's all comes in different formats. All of the dates are different, different formats. It's kind of messy. Sometimes they're text files, sometimes they're CSVs. It's all kind of complicated. But anyway, regardless, there's a lot of data there. And what we wanted to do was to come up with just a number of how many people have had, say, one particular ICD-10 code, which could be mapped from SNOMED for all of the different, what we call chapter levels of ICD-10. And so that's 1,844 different analyses. That's A01 to Q99. Those are ICD-10 codes, and running against 70 million rows of data. And once we used polars, this sped up from like a long time to 84 seconds. So we were going, previously it was being clicked through on a pandas notebook, or a Jupyter notebook, but it was running pandas. We don't have an exact count how long that would take because it really varied, because we were doing a lot of loading of data every analysis, and you could stop and start. But essentially, it's a huge speed up. 84 seconds to run the whole thing is a huge speed up. Okay. All right, so how did we do this? So very cool thing that I hadn't come across in polars is it has a really sophisticated way of dealing with different types of dates. And so you can feel my pain here if you look at all of the different dates that I had to deal with. This is just from the NHS data. So all different ways you could represent any particular date. Some are timestamps with times, some have dots, some have slashes, some have dashes, some are just, like the actual date. And there's a sophisticated way that you can just like essentially coerce it into a date that has a standard format, as long as you sort of roughly know what it is. So that's a really cool feature of polars, and I think a lot of people will get used out of that because we all deal with messy data. The other thing I did was after I cleaned the data, I used polars, and to be fair, you can do this in pandas as well. I saved it as an arrow file, so it was optimized for loading again. And it just means that we can just load the data directly from the binary. It doesn't need to be copied, doesn't need to be converted, and that makes it quicker. So we've got a nice clean copy of each data file and the whole thing merged together. And then I used the singleton design pattern. So that just means that I was just essentially storing each data set once and creating a list of that. We weren't having to do it per analysis, and that saved us loads of time. Okay. And then I just filtered. So I didn't do any merges, I just did a filter. Okay, so that's how I ended up using polars, and there's more work to be done on this. I'm about to start some work on quantitative traits, so that's measuring things like continuous values like blood pressures, and we're going to be extending this, and I'm really looking forward to that because I think polars has got so much functionality. We can definitely make it a lot quicker, okay, and a lot more robust. So I'm now going to talk about Rust. So I already knew Rust before I started using polars, which I appreciate isn't everybody's journey. But I do think it gives me some insight into why Rust is great, and why polars have, been able to write it in Rust and why they have done that. So Rust is a system programming language. It focuses on speed, memory safety, and concurrency. It's a compiled language, and that means that it compiles into a binary format that runs rather than being interpreted, and I've got a diagram to show that. It's most similar to C or C++, certainly in terms of performance, and I think some of the features are probably C or C++ sort of esque. And certainly in the way it deals with memory is more towards that than, say, Python. Okay, so I said it was a compiled language, and what is a compiler? So a compiler it takes source code, and so that might be in your Rust, and then it compiles it into machine code, so that's your program, and you get a binary program, which can then run, and then you would get a result. Whereas something like Python and R, I imagine, is similar. It's an interpreted language. So it's essentially, if there's an error in your code, you only find out when you get to that bit in the code, unless it's something, like which will make the program not run at all. And that can mean that you can write quite unsafe code, and you don't realize that there's bugs in it until you hit that part. That part of the code. Whereas in Rust, that's just not an option if your code has got errors in it. And I'm talking about errors which just make it not run, not that you've implemented the business logic incorrectly. I mean, there's just an error in it. It's not going to run. And you'll know that immediately. Okay. And actually what's really good about it is it gives you a really useful error message. So sticking with Python, I'm going to write a function which adds two numbers. Okay, so this is just an example of Python and the problems that you can have. So if I run this 4 times, call this function 4 times, I can add two numbers together. Okay, 5 and 10. I'll get 15, you would expect that. I can also add some strings together. So if I have 5 as a string and 10 as a string, it will go to 510 as a string. Okay, but if you try and mix and match, so 5 as a string and a 10 as an integer, you'll get a type error at runtime. Okay, so this shouldn't really have been allowed. You can add typing into your Python, and lots of people do that. Not so many data scientists I've noticed, but I think we should all do that. But actually, it's not strictly enforced, so it's not a strongly typed language. So in this example, A can be both a string in one time, or it can also be a number in another time, integer or a float. So you've got lots of options, which is not necessarily the right. You're nice and flexible, but it's not necessarily the best way of doing it. Okay, but anyway, in this example, you'd get a type error. Okay, and it gives you some information. You can't concatenate a string to an int. Okay, but you only get it once it gets to that point of the program. Whereas if we did exactly the same thing in Rust, basically it will just refuse. So you have to say within the the definition of the function, what type of data you're expecting. So I've put I32 in this example. So even though, yeah, you might want to concatenate a string 5 and 10 together, because it isn't, it's found a string rather than an integer, it just will refuse. You'll get a compile time error. And the same thing if you try and mix and match the different types. Okay, so you'll get, again, an error. Okay, and actually, I will just say you get very useful compiler errors that give you useful messages. One of the things when you're starting out, especially if you come from like a more flexible language like Python, you get very annoyed with the compiler. It's like fighting the compiler. But actually, if you just lean into it and use it to write better code and to learn how to use Rust, I'd really recommend that, because there's some seriously sophisticated programmers behind Rust who've put in a lot of thought about how the compiler can be useful. So we should definitely use their brains to improve. Okay, so I'm just going to talk a bit about memory safety. I will preface this by saying I'm not a memory expert. So memory safety. So one of the things you'll hear all the time is about how Rust is memory safe. Now, like with any other language, you can write unsafe code. I would say in Rust, it's memory safe by default. And if you want to write something that's unsafe, you actually have to mark it with like unsafe in the code. So that's helpful. But anyway, let's talk about memory safety. So there's different types of sort of memory safety or things that you might try and do. So there's accessing unallocated memory. So this is when you're trying to read or write data that hasn't been assigned to your program. You've got buffer overflows, and I've heard about them being used quite a lot for malicious attacks or when there's been sort of a breach of some kind. You've got use after free. So this means if you imagine you've got I've just put a little chest of drawers there to demonstrate it. Imagine you've got your data in those drawers. It's like accessing drawers after they've been given back to the system. So the contents are no longer guaranteed to be there. And then dangling pointers, which is holding onto the address of the drawer that's been reallocated. So you might have like unpredictable behavior if you do that. Okay, so one thing I will say, if you come from like a Python background, and again, R I'm sure is similar, is you don't generally think about these things because it's like, oh, it's great, it's so flexible, you can just do whatever you want. You don't have to think about memory in the same way you would for like C or C++. But that's because the Python interpreter's doing it for you. And it automatically is allocating memory to stuff when you, like to variables, when you create a new object, for example. And it is then going behind you after you stopped using that and deallocating that memory. Okay, and that takes time. And one of the big performance improvements with Rust is that that doesn't need to happen. Okay. So, because Rust has been designed with sort of memory safety in mind, it has these very strict rules at compile time. And that basically prevents all of these horrible issues that I mentioned before. It does this through an ownership system. I'm not going to spend a lot of time on this, but essentially like data or information belongs to like variables, and you can't necessarily share them, or you can transfer ownership or you can borrow it. And there's strict rules about how that works. Okay, and that is probably, I would say, like the most difficult part when you're a beginner of getting used to in Rust. But use the compiler as you know, it will try and help you where it can, especially if you're writing relatively simple programs in the start. Okay, that was my icon which showed memory the garbage collector. Okay. All right, so this is a Python example which just shows you that stuff can be unsafe, and it's something we don't think about. So for the data scientists out there, I'm just going to use an example of a nested dictionary, and say I've got a dictionary which has a key and a value, and then I put that dictionary in another dictionary. If I then modify the original dictionary, it does end up modifying the one that it's been put into. Okay, so you get a modified value. So that's not necessarily that unexpected, but it can cause problems, especially if you've got complex data. And I sort of think it shouldn't really be allowed, or it should at least flag it to you. If you're trying to do something in Rust like this, where you are attempting to place one object inside another object, a hash map is the same as a dictionary, essentially, in this case, just sort of broadly, it's going to give you a compile error. Okay, so it's going to say map1's value was borrowed and it can't be modified until the borrow ends. Okay, and it will just refuse to run. Like, you don't even get the option of finding out that this is an error in production. It just will not compile. Okay, and this is just to demonstrate what the compiler looks like. And as you can see, it's got some really helpful things. It's saying, why don't you clone this? This value has been moved, and that means it's just been used somewhere else in the program. And you have this idea of borrow. Again, I'm not going to go hugely into the borrow, but that's something which tricks a lot of people in the beginning, but is also an amazing part of Rust. Okay. I am probably just going to skip this slide, actually, and we're just going to talk about parallelism. So in this example, we've got I've got a main function. We are again using the datetime to just do some measurements, a start and an end to get a duration, and then we're saying for 1 to 5, can we sleep for 1 second? Okay, and so that's going to do it 4 times. Okay, because we're indexing from 0, so we're going to have 4 loops and we're going to have 4 sleeps, and unsurprisingly, that ends up being 4 seconds, a little bit over 4 seconds because there's a bit of a starting cost. Okay, if we do that in Python, we can do this clever thing where we create threads and they can run in parallel, and then we join them back together with like a handle which joins together, and we'll find that we've done exactly the same thing, but it's taken 1 second. Okay, and that's because they've happened at the same time. Now, we have done a little bit of extra coding here, and actually you can do something similar in Python, but it's not really built for that. There's been lots of work put in to try and improve that aspect of it, but Rust kind of just does it out of the box. Okay, so that's just a brief introduction to Rust. Hopefully it's got you interested. You've got polars, you can see some of the examples that we've used. I've used it for, and then we've got an introduction to Rust, and hopefully you can get started. I would recommend, if you are using pandas at all for your data science, to have a go at polars. You'll notice that the API is very similar. I think that's done by design, so that you can do that switch. So, in theory, it could be quite a easy and pain-free switch over, and you could do it piecemeal, bit by bit, and just see what performance improvements you get. That's the docs again, and the makers of polars have put in a lot of thought into the docs, so I recommend you check them out, and there's some great tutorials online also, and that's it. Thank you very much for listening.